Hello, everyone, and welcome to Kinematics with Teacher Felly. Now, what is kinematics? Well, simply put, it is a branch of classical mechanics that describe the motion of points, objects, and systems of groups of objects without reference to the causes of motion. These causes of motion being things like forces, your gravity, your friction, right? Of course, also tension. Now, kinematics has a more straightforward approach when it comes to motion. Why? Because unlike your physics that put into account things like tension or other causes of motion, it has a more mathematical approach to it, as we can see later, which is why it is often given the moniker or the name of geometry of motion. These are the key concepts that we will be discussing lightly today. First, we have displacement. Second, we have velocity. And the third, we have acceleration. Later, we can see that not only do they affect each other, but they have a very interesting mathematical connection. First, let's take a look at displacement. Displacement is, simply put, a particle's position change with respect to a fixed point at a particular instant. It is a vector quantity. And when we say vector quantity, it has both magnitude and direction, as learned in your physics classes. It is still very much the same in concept. Now, if S, which is often the representation of displacement of a moving particle, let's say P, from a fixed point O at time t, we have the following interpretation. If S is greater than zero, the particle is stated or stationed in the positive S axis. If it is equal to zero, the particle then is stated or stationed at the fixed point O or zero. If S is less than zero or is negative, it is therefore on the negative side of the S axis. Now, what does this look like in practice? Well, Watson travels from fixed point O along a straight line. It is its displacement from O, which is S meters, at time t seconds after passing O, or its fixed point O, is modeled by the following equation. S, or displacement, is equals to 16 t squared plus t cubed for any instances where t is greater than 0 but less than 4. Now, although this does feel like a handful, we only have to remember that from any fixed point O, displacement will always be represented by S, and time will always be represented by O after passing the origin or where we began, which is point O, and is modeled by the equation often given in the problem, which in this case is S is equals to 16t squared plus t squared plus t raised to 3 or t cubed for any instances where time is 0 to 4. If you don't follow, let's create a simple table as shown in this, where we have two rows, which represents t, which is time, and displacement, which is s. Now, when in order for us to solve s given t, all we have to do is substitute t for its value to the given equation, where we can see that when t is equals to 0, we have a displacement of 0 because we only substituted. When t is equals to 1, our displacement therefore is 17. And when 2 is equals to, when t is equals to 2, our displacement is 72, and so on and so forth. In order for us to find the displacement at any given time, so we will only have to substitute t in order to get s, which is our displacement. Given that we've already discussed about displacement, now let's talk about velocity. What is velocity? It is the rate of change of displacement. Now, from that alone, if you remember the rate of change, what do we say when we say rate of change? It is the derivative of something. In this case, velocity is the derivative of displacement, as it is often represented by d of s, ds over dt, where s, of course, stands in for displacement of a moving particle at time t. It is a signed vector quantity. And when we say signed vector quantity, it, of course, it retains the magnitude and the direction. But now the sign actually matters. Its sign doesn't just simply state where it should be put on the s-axis. Now it actually means something, which for any particle with a velocity v, we have the following interpretations. If v is positive, or the velocity is positive or greater than zero, the particle is moving in the direction of the positive axis, which means it's moving toward where the positive side is. If v is equal to zero, then the particle is instantaneously at rest, which means that it is not moving because there is no speed, there is no velocity. Now, if velocity is less than zero or is negative, the particle then is moving in the direction of the negative s axis, which is most often than not to the left. Now, let's try our hands at a sample problem. Of course, we learned earlier that velocity is simply the derivative of displacement, which means that with the same problem, with the same given, we can solve for the velocity. All we have to do first is digest the following question. Find the velocity of Watson after 4 seconds, which means that our value for t is going to be 4 when we solve for velocity. Now, given that we only have the equation for s, what do we do then to get the equation for velocity? Simply put, we take the equation and get its derivative. What you see on board, which is t multiplied by the quantity of 3t plus 32, is a simplified version of the actual derivative. This is done so for visual clarity during this video. However, another way we could put the derivative is 3t squared plus 32. Now, with that said, we substitute the value of t to the equation. And we know now that the value of t is 4 because we're finding the velocity of Watson after 4 seconds. We simply put in 4 at any t, and we have the following velocity, which is 176 meters per second. Now that we're done with velocity, let's talk about acceleration. It is the rate of change of velocity. There we have it again. The rate of change, which again implies, or rather explicitly is, derivative. Simply put, acceleration is the derivative of velocity. And we learned earlier that Velocity is the derivative of displacement. Thus, acceleration is the second degree of derivative or the second derivative degree of displacement. As such, when solving for displacement, velocity, and acceleration, so long as you have one equation for any of the three that I've said, you can solve for the others through integrating and deriving the formula to get the appropriate equation, often represented by dv over dt, where v is, of course, the velocity of a moving particle at time t. The same as velocity, it is a signed vector, which means it has magnitude and magnitude and direction, as well as its sign being positive or negative has certain implications. In this case, for any particle with acceleration a, if a or acceleration is positive or is greater than zero, that the particle is speeding up or accelerating in speed. Now, if a is equals to zero, the particle then is traveling or moving at a constant speed, which means there is no acceleration. Lastly, if a or acceleration is less than zero or is negative, the particle then is slowing down or decelerating. Of course, now let's try to apply this, right, with the same given in this problem. However, this time we're going to do something a little bit different because last time we solved for displacement and we solved for velocity respectively. Now we're going to find the value of t when the acceleration of Watson is instantaneously at zero. Let us first digest this. We're going to find t when acceleration or a is equals to zero. Therefore, we take the equation. In this case, we can take the second degree derivative of s, or we can simply take the derivative of the acceleration of the velocity that we had earlier, which is going to be 6t plus 32. What we're going to do now is instead of substituting p, we're going to substitute a, which will give it 0 is equal to 60 plus 32, which would then simply allow us to isolate t and find its value there. And we end up with a value of negative 16 over 3. Now, it does get a little bit tricky because, as we know, time can't be negative. However, with certain interpretations of problems, there can be such a thing that this simply took or this simply happened before we took time to account, right? However, in this problem, since we had that when time is zero, we are going to be at our starting point O, which is zero. Therefore, we had not moved yet because we're still on our starting point. Thus, when we have negative time in the context of this problem, it means that there is no point in time where Watson is traveling at a constant speed, which means that as we have seen earlier, the greater the time increases or the further the time is, Watson accelerates and accelerates, which means he cannot simply travel at a constant speed. Of course, that is only given the context of the problem. With that said and done, thank you for listening and thank you for being here today with Teacher Feli on kinematics. See you again. Bye bye.